So my name is Pillgram Larsen. I work in the tools team at LinkedIn. The tools team is responsible for the entire software development lifecycle at LinkedIn. And specifically, I work in the development tools team. Our responsibility is for the development environment. There's a separate team that's responsible for taking the developed software and provisioning it. And I wanted to start off with what are we trying to do? What is this mission that we're on at LinkedIn when it comes to tooling and software development? It really is to radically change the definition of how software is developed. I got into tooling about 3 years ago at my previous company because I've been working as an application developer for exactly 4 years. 4 years is significant because that meant I went through 2 release cycles, right? I'm not sure how many of you have ever been through release cycles where it's 18 to 24 months in between you release software. And then it becomes really, really expensive to talk about this feature either going in the release or not making it to the release, because if you miss it, hey, it's 2 years till the next time. So the releases get pushed out and pushed out because you need to cram this one other important feature in. And managers and engineers spend an inordinate amount of time arguing about what features to put into the release. And then you get to the point where you're trying to do the release and you have a very complex merge chart. You have a project in itself just trying to merge all the feature branches into the release branch and get it all stabilized. So I wish I would say that the first time I went through that, after 2 years, a light bulb went off and I'm like, this makes no sense at all. But it took me 2 cycles. You know, I was just out of school. Didn't really think to challenge the way things were done. And that's kind of that's where we are. There's this status quo in software development at the macro level when it comes to releases. Then at the micro level, every time a developer is trying to develop some new software, you go on your very high, powerful machine that, you know, we've proven that every single machine, even the mobile devices we walk around with, has enough computing power to send us and land us on the moon. We go and we type on those, and while we're typing, this very powerful machine is sitting idle. It's not doing anything. And then we decide we're going to ask it to go do something, and then we sit idle waiting for the machine to go do it. So there are inefficiencies everywhere in the system, and everybody's just come to accept that, you know, that's the status quo. That's how we develop software. So in development, at LinkedIn, we want to radically change the definition. We want to eliminate these inefficiencies in the system, both when it comes to releasing software and when it comes to developing software every day. That's what we're trying to do. So I think there's a lot of buzz around continuous delivery, continuous deployment. We have some ideas around that. And I think Gradle is really instrumental on the development side, on the micro level, on the day-to-day. How can we eliminate these inefficiencies in the system? So what I'm going to talk about is, first of all, what is this software diversity that we have in a large enterprise like LinkedIn? When I came to LinkedIn, we were around 1,600 people at the company. That's 2.5 years ago. Now I think there's about 5,500 or so. So really, as we've had gone through this hypergrowth phase, so is our diversity. I want to talk a little bit about that and the challenges that it brings, and then talk about how that diversity fits in with build automation. Because at conferences, we talk a lot about Java, we talk a lot about Android, very specific high-level platforms, and those are really important, and those are where a lot of the work goes on. But there's other very important edge cases, and I find that every single enterprise have these edge cases that we have to integrate with. And talk about how can you integrate those at different tiers, at different levels of integration, and what does that mean? And then finally, talk a little bit about, I think you guys have been hearing a lot over the last 2 days about new features coming in Gradle, distributed builds, the new configuration model. How do those features, how did they come about, and how does that fuel this drastic change in how we think about software development and software releases? So LinkedIn at its kind of front is a very standard software development enterprise. You know, it's your Java, your Jetty, Tomcat, Spring, you know, the JUnit, TestNG, JavaScript, HTML, CSS, very, very standard stuff. And all the standard tooling, your IntelliJ IDEA, your Eclipses, your Gradle, and not a lot of Maven, but it could certainly be Maven, but very standard stuff. And really, it's amazing to me how many times the 80-20 rule just happens in nature. And if you look at it, it's really 80% of very, very standard stuff at LinkedIn. But at a certain scale, 20% is still a lot. There's still a lot of stuff going on with the 20%, and that tends to drag an inordinate amount of time and resources with it. So we need to think about that. So every request that hits any LinkedIn product hits multiple non-JVM, or even, I should say, non-Java services, but also non-JVM services. They go through an Apache traffic server layer from C++. It might hit a Node.js server somewhere. Thank goodness for service-oriented architecture, right? It might hit some service that was brought in through an acquisition that's running Ruby on Rails. And you know, in the end, it hit some database storage layer through JNI and C++, right? So these become really, really important pieces of your stack, and you need to think about them when you're doing software tooling. And then, of course, there's your mobile applications. Android, you know, being at this conference, at the Gradle conference, obviously Android is well understood. iOS is also well understood, but it doesn't really play well with the other paradigms of software development. So I'm going to talk a little bit more about about iOS later. And then I talked a little bit about acquisitions. We try to integrate acquisitions into our development stack, but there are going to be other programming frameworks, and the larger the acquisition, the harder it is to integrate them. And then simply at scale, one thing I've found again and again, once you hit a certain scale, you're going to need some C++. You're going to need some native code. Because there's certain things that are latency sensitive, that are jitter sensitive, that you just need to be able to do in that. So what we did for this talk, we actually, this talk kind of fit well in with the intern project that we're having right now, is we started to look at, okay, what languages, what frameworks do we have at LinkedIn? So we just looked at the pieces of code, the code bases that we manage in the LinkedIn tools team that we know about. There's a whole other shadow world that we know we don't, or we choose not to know about. We could have mapped that too, but we didn't really want to know. Just in the stuff that we know about, that we manage, that runs through our tooling, there are 60 different programming languages. And there are, you know, once you get into this section down here, you know, there's stuff there that I didn't know existed. I mean, there's a lot of stuff I didn't know existed. There's stuff I had to go to Wikipedia and look up and, oh, that's this programming. Yeah, that's a real programming language. So all kinds of things. I mean, 60 to me, that came as a shock. Like, that is a ton of different programming languages. So you really have to take this thing seriously. So one of the things we did, and one of the things I talked about here at the Gradle Summit 2013, was we built a tooling layer on top of this, on top of the tooling, on top of the build tooling, on top of the programming languages, on top of the frameworks, called multi-product, which is a set of tools and processes that's architected for this heterogeneous world of software development. So you can plug, it's essentially a pluggable architecture where you can plug in any build automation framework, deployment framework, SCM framework. We're crazy enough to where we don't even have one SCM system at LinkedIn, so we needed to have that. Not something I recommend. And then we started thinking about what were some tasks that all software have to go through. There has to be some kind of build step or phase where I take the raw code and I create an artifact of some kind. Yes, we debated very heavily, should we have a test phase for everything? And thankfully, I think we ended up with yes. Yes, everything should be tested at the level of the code. And then, you know, releasing, publishing, deploying, provisioning, etc. So I gave a whole talk, as I said, there was a Gradle Summit 2013 and then at Twitter a while back on multi-product. If you're interested, the link is there. If I ever get around to uploading the slides to the website. The key concepts in multi-product is we want to group code together. Different programming languages, different programming paradigms have different ideas around what is a unit of code, right? A jar is a unit of code, but a jar could actually be a fat jar containing other jars, right? We wanted to have a very clear and concise idea about what is a unit of code. What is a set of code that has a set of public APIs and a set of internal code to provide those public APIs. So we group things together by SCM repos, and we can version, we can publish, test those as a unit. And then we needed more metadata. I think this is something we started talking to Gradleware about. Adam mentioned it this morning. I think Daz mentioned it in the native talk. There's simply, Ivy and Maven do not have enough metadata richness, or in some cases has way too much metadata flexibility to really work in the real world. You need more, you need simpler ideas around metadata to say, this is where this came from, this is what it does, this is what Java version it was built with, or this is what programming language it is, this is what type of artifact it is. So we needed to build that on top. Hopefully, Gradle will provide that stuff in the future and we can get rid of our metadata layer. I mentioned the pluggable implementation of subsystems. Version management is really key. I think I've seen just about every version management scheme possible, and some that aren't really possible. And the one that's very common in the open source world is, nah, who needs version management? I'll just replace this thing with the same version or without a version, and if I break someone, it's not my problem. So we use semantic versioning. We have real semantic ideas around what a version means. You cannot override an already published release version, etc. I also happen to think that snapshot versions are a really bad idea for anything besides local development, but I'll talk about why I think that's even a bad idea for local development. And then, so once we have this tool set, there were two things we could do. We can focus on developing software very efficiently, and we could focus on releasing and deploying software very efficiently. And we started with releasing and deploying. So a lot of what I talked about here last year was how do we release and how do we deploy, totally automated for any software language framework underneath the hood. And we've gotten very, very good at doing that. So we have full continuous deployment, full tooling around that at this point. So what I want to talk about this year is more around the build automation, but I'm happy to answer any questions around continuous deployment once we're done in the Q&A part. So build automation. First of all, the term build, I struggle with the term build in this context. I think we need to change that term, because the term build to me, when I came up doing software development, was you would compile, you would create something. And that's now just a subset of what we're talking about here. When you think about unit testing and provisioning and metadata and all these things, there's so much other stuff. You can do anything with the Gradle task. So it really, I'm not sure what to call it. I don't have a good idea, but I think we should call it something else just to distinguish this new world from the old world. But that's really what I'm talking about, is doing something to code in an automated fashion. That term, or build automation, that concept at LinkedIn is mostly synonymous with Gradle. When I came to LinkedIn 2.5 years ago, we were using Gradle 09 something. It's very, very early days. And then Gradle had already been at LinkedIn for quite some time. We went through the whole 1.0 milestone fiasco. And now we're very happy that we made that decision. And really, over time, we keep rolling out Gradle everywhere because of some of the benefits that I'll talk about. That really is true today. LinkedIn and build is in most cases synonymous with Gradle. So when I talk about scale, you might have heard in some of the talks they'll refer to LinkedIn's like huge monolithic project built with Gradle. So what is the scale we're talking about when we talk about this large project? So there are 4,000 projects in a single multi-project build, single multi-project Gradle build. If you want to run the build, it's a little, actually, I just ran it this morning. Before this task, it was 71,118 tasks or something like that to run the build. Doing so, the daemon chews up about 32 gigabytes of memory. That's down from when I was here last year. It was not possible to do on one of our 78 gigabyte of memory machines. So I'm not sure what it's down from, but it's down from more than 78 about a year and a quarter ago. It takes, Adam talked about it this morning, so it takes about, Gradle configures everything if you run a full build. So it takes about 4 minutes to do that on one of these pretty much the most powerful computer servers that you can get at this point without building something custom, which really is unfortunate when you're just trying to do clean and you're configuring for 4 minutes just to be able to clean. So if you do the full build, it takes about an hour and 15 minutes, which is pretty darn good when you think about it. That's really, really good. And some of these tasks are, forking off JSP compilers that then go off and do full builds of their own. So very, very complex build. We're super happy about how Gradle is performing, but we think we can take it to the next level. And now you might be able to tell why we did some things like configuration on demand, etc. A lot of this lazy loading. Why the configuration model, next generation configuration model, is so important to us. By the way, we don't think this is a good way to develop software. We don't recommend this approach, but sometimes you're just plopped into a situation where you already have this, and I know several other enterprises that have the same situation with large monolithic repos. But it's something we're actively working on pulling it apart. So when I talk about integrating or build automation, what naturally came out of that at LinkedIn, we had 3 different tiers. Complete integration, partial integration, and orchestration and delegation. I'll talk about what each one of these means to us at LinkedIn. So when we think about Gradle, in the core, there are 2 equally important engines. There's dependency management. How does code, how do projects relate to other projects, artifact relate to other artifacts, and the whole dependency graph, as well as the task graph. How do tasks relate to each other, which tasks require what inputs, outputs, which tasks are up to date, how many of these tasks can I run in parallel when can I execute a task. Each one of those concepts is incredibly powerful. You can imagine lots of use cases where you just want to resolve the dependency graph and use that. Unfortunately, you can hack it today, and we do sometimes, where you have Gradle spit out the dependencies to a file, and then we'll read that file in from something else and use it. But it's not really, unfortunately, the dependency engine, Gradle's dependency engine, is not standalone today. It's more or less coupled with Gradle core. But the task management is standalone from the rest of Gradle. And that's incredibly powerful. Just to be able to have a parallel and hopefully soon distributed task management and execution engine with up-to-date or incremental logic, with dependencies, with parallelism all baked into the graph. It's not conceptually a hard thing to do, but it's really hard to code it up and get it really functional like Gradle has. So I want to just separate out those 2 concepts because we do use them a lot. So I figured, Baron, you would enjoy the Snoopy here. So figured I had to have at least one Snoopy picture for Baron. So what is it? What do we mean by complete integration with the build system with Gradle? So Gradle manages the build using the Gradle dependency engine and the Gradle task management engine. Right? Gradle understands the structure of the code you're trying to build and the relationship between that code and other code. These are both things. It really is semantically aware of the project that it's working on. And these are your standard, the things that you think about when you think about Gradle. Java, Scala, Groovy, C++, Android. Things where you can declare your dependencies in the Gradle syntax, and you can execute tasks and apply plugins in the Gradle task management, and Gradle will execute those. It is a little bit of a fuzzy line because at some point Gradle, either spawns off Zinc or Java C or Scala C, whatever it is. It's not like Gradle actually runs the compilation or creates the jar artifacts by itself. But the integration is so rich, so deep that you really don't worry about it. You don't care about that. It all works. So that's what I mean by complete integration. So partial integration, there are very few projects at LinkedIn that have complete integration, unfortunately, because you're integrating something, and this one's a big one, right? As soon as you add some resources, as soon as you add some JavaScript, you add some HTML, CSS to your project or to your multi-project build, to your application, you suddenly have this opaqueness, this black box. It's like, that doesn't have, you don't do dependency management anymore for JavaScript. Or if you do, it's because you have really good conventions or you have a very simple build. But it really is, at this point, thinking about, you have some black box, some project or some dependency that's a black box to you. That's what I mean by partial integration. Most of it, hopefully all of it, or close to all of it, Gradle understands, but there's some pieces it doesn't. And as soon as you do that, you start having points in your build where things get harder to reason about. Doing the IDE integration, incremental tasks now become at a higher level, at a macro level, right, versus really understanding the lower layer structure or semantic of the code. And it becomes a lot harder to reason about. So this is what I'm talking about when we have our large build. We go off, we compile a bunch of Java code, a bunch of Scala code, and suddenly we get to JSPs, and it's just fork and go do stuff. And if anything changes, any JSP, right, we just fork and we go do stuff, and we eat up, 12 cores and 5 minutes and a couple of gigabytes of RAM doing stuff. But we don't know. Gradle doesn't know what it's doing because the integration, it's a coupling in that integration layer. So pretty soon when you get to a kind of real application, will you have this kind of partial integration. Another one, Hadoop is huge for LinkedIn, the personal web, personalization. If you're familiar with LinkedIn, you might have seen people you may know or groups you may want to follow or companies you may want to follow, etc. All of this kind of personalization based on your preferences is an incredibly powerful tool of the personal web. So Hadoop, crunching through those on the back end is very important. We don't have very good tooling, or Hadoop doesn't have very good standards to manage that. LinkedIn uses a homegrown but now open source tool called Azkaban to manage Hadoop workflows. But at its core, it's really MapReduce and UDF's user-defined functions are just Java. So they do get compiled into jars. But then you have special programming languages, Pig and Hive, scripting, and kind of a SQL-like language that then gets mashed together into a Hadoop job. And then you have multiple Hadoop jobs that get mashed together into a workflow, a staged workflow that then gets uploaded to Azkaban. So that's another example where you have some stuff that Gradle understands deeply and some that it just is a total black box. It just does something with it. and then you lose a lot of this power of Gradle. Yeah?
When you say logic
So we drive, it's a good question. We drive the build off of Gradle's task engine always, right? So, but some of the tasks are actually spawning off another tool or another framework to do something, right? It's not Gradle doesn't understand what it's doing. It just knows I need to fork the JSP compiler. I need to zip up these scripting files. And now the problem is when you have that kind of loose integration, for example, if one of the files change, you have to redo the entire task. So they become bigger tasks instead of smaller granular units. That's what I mean by partial integration. Yeah. So then naturally, the third one is Gradle doesn't understand the build at all. Gradle is just the orchestration engine. It's just a task graph. It knows it needs to go do something, but it doesn't understand what it's doing. So this is perhaps my favorite graphic of the whole presentation. I don't know if we have any of the Android guys or something in here, but that's I'd love to have that on a T-shirt. It's just whoever came up with that, kudos. So Gradle now just starts managing one or more of the underlying systems, right? It could be one. Typically, it's more. Gradle's gluing together multiple underlying systems in order to accomplish something. Gradle does not understand the structure of the code of the project, of the multi-project build, of the application. It just knows it needs to go do something because you've told it what to do. So one example at LinkedIn for iOS, we use CocoaPods, and then of course you have to use Xcode, and then we use Gradle to kind of glue it all together and talk a little bit more in depth about what that is. And then also for C++ today, I hope to use Gradle with a kind of complete integration here in the future. But right now, there are some gaps that we need to solve in order to use Gradle for native code at LinkedIn. So we use CMake, Ninja, gperf tools, and then kind of Gradle again to wrap it all. So that's what I mean about Tier 1, Tier 2, and Tier 3 integrations. So why do we care about these? I've alluded to it through the whole way. I tried to give examples of why we care about it. We see correlations with the performance. The higher up you are, the more Gradle understands about the code, the more performant it can be, the more scalable it can be. So I mentioned there's no way without Gradle understanding deeply the logic in our largest build that we could do that. Things like configuration on demand, all this lazy loading is needed in order. We cannot simply keep the daemon up and running with 30 to 40 gigabytes of memory at all times. That will not work. The developers find it easier to use if they have a common terminology. They're more productive if they understand the structure of the code. If they have a common set of terminology, they can use the build logic as a view into the project structure. So we see a strong correlation to productivity and productivity metrics the higher up something is integrated with Gradle. Stability and maintainability is another big one. So we have Yarick back there. He's hiding right now because I mentioned iOS. That's one of the things, right? We go off, we spawn off something and it fails. And we don't know why it fails, right? The simulator hung or Xcode hung or something went off and did something. It's harder to create stable code, get the exceptions back, understand what's going on. If you have the semantics of what the structure is, what the code is, what the task is doing, it's much easier to debug and figure out what's going on and write stable and maintainable code. So then naturally, the goal that we've set for ourselves is we want to try to push the integration higher. And at the same time, we're trying to tackle the kind of the tier 1 or the complete integration. How can we make that better, faster, smarter to get more and more benefits and try to push people to integrate at a higher level. It's always kind of a push and a pull model. If you just by edict say you must do this, people might do it, but they'll do it grudgingly. If you can show them why the benefits are there, they'll try to do it on their own. And that's been very successful. So how can we push integration up the stack? How can we get to higher levels of integration? We've heard that, and I'm super happy, several people from Gradleware, from industry, throughout the last 2 days have mentioned JavaScript. I lumped JavaScript in with other resources, web resources that we at LinkedIn at least use the term static content for. So Doesnt templates, Sass, CSS, HTML, JavaScript, etc. These are all, we lump them into static content. It's the next big thing we got to figure out what to do with. How can we have reasonable dependency management, code reuse, modular code, know what we're using when we need to change something, versioning schemes, etc. There's a lot of stuff going on. There's actually, it's this typical tooling lifecycle where right now there's so many tools. The hard thing is to figure out which one's going to win, which one's going to have the best paradigm. You have your Grunt and your Bower and your etc. going on. So LinkedIn is working very actively in this area right now. We're trying to figure out how we can do it, and we will try to talk a lot more about what conclusions we came to, and hopefully they'll be successful. We need to encourage certain commercial partners to think about the software development lifecycle. So I know there were some folks from Apple here this week. I don't know if they're in the room, but really as good as the iOS or the Mac integrated user environment as once you've deployed something, once you're running something, as bad the Apple developer lifecycle is. And everything from trying to get a new device or a new key from Apple or a new device attached to your key to integrating with code reuse, modular code, sharing libraries, open source. It's just awful. So hopefully we can get some of those things fixed. And there are other commercial partners out there who would be great if they could improve their tooling and their tooling support and their development support. And then this goes kind of with the static content. We need to find reasonable standards, well-working standards for certain things. I think Hadoop is in a state right now where it's not going away anytime soon. It is a really, really useful tool. It is a kind of an industry standard. It needs to have a reasonable amount of processes, standards attached to it to say this is how you should develop, these are the languages, these are the tools we should be using, these are the things we can do to make it really run. So out of these three, number 1 and 3, LinkedIn is investing very heavily in right now. Number 2, we would like to invest in, but there's not a lot we can do without the support of our commercial partners. So how can we make the Tier 1 integration faster, smarter, and better? So one thing, through our partnership with Gradleware, I don't know if any one of you even noticed, but starting with Gradle 1.10, if you changed a single Java file, you would end up with a single class file changing as the output. So if you went and you changed a Java file, you ran Gradle compile Java, only one class file changed. Prior to that, 1.9 and earlier, Gradle would blow away the entire output whenever something on the input changed. That was very important to us because we use JRebel. And so when you blow away the entire output and then recreate the entire output just with that one class file that's changed, JRebel had to reload the entire thing. And then we just discovered, hey, there's a lot less memory usage. It's a lot faster if you just do this. So we can do things like that when we understand the semantics of the build. When Gradle understands .java files and .class files in the inputs and outputs, it can do more intelligent things. So that's something that's already out there and already working. So it's interesting when I talked about the memory usage of our very large build. That's actually ever since, I think we went live on Gradle 1.8. Ever since Gradle 1.8, we've seen a nice downwards linear trend for every Gradle release. Memory usage gets a little bit better. So that's been awesome. One thing we're really excited about, and this comes back to what I talked about in the beginning about when you're, as a developer, you're typing some code, you're changing some code, your machine is sitting idle. If any of you are familiar with Play or SBT, it has this concept of a continuous mode where it's running in the console, you change something, and it immediately detects that it's changed through iNotify, and it goes and it runs and kicks off the tasks related to that. So if you think about that, right, in Gradle, that would just be analogous to continuous task execution. So some input changed, so I know what tasks to go run, and I'll run those. And that actually just takes care of 80% of the development iteration. You're changing something. Now you can integrate that with IDEs through the tooling API that we heard about earlier today, and you can start having all of these nice things that for developers, they don't even think that it's a possibility until they've tried it, and suddenly it transforms the way that they work. Truly parallel builds. So this is where the new configuration model comes in. Unfortunately, with the existing configuration and model in Gradle, they cannot just parallelize it because it has to be computed up front before they can start parallelizing. So new configuration model is important. And then having inter-project parallelism. So today, I don't know if you are aware, but if you have two projects in a multi-project build, only a single task from each of those projects can ever be executed in parallel. So having that, so you have inter-project parallelization today, but the intra-project parallelization is missing. And then once you have that, once it's truly parallel on a single computer, you have a model that you can distribute, then you can distribute the build. You can just say, okay, if it helps, I can put two machines on this, executing this build or this task graph, and off you go. So what do we have today at LinkedIn around Gradle? We have actually now a large and growing set of Gradle plugins. They're mostly, or they're all internal today, and they're mostly useful internal. There is some stuff that once we figure it out, once it gets to a clean state, might be worth open sourcing. But mostly it's taking Gradle stuff and making it, adding customizations for LinkedIn's environment. Just we do things a little bit different. I talked about grouping things together into a single product, etc. Adding some custom artifact types. So we have our own database framework. So we wanted to add our own database patches, etc. Those are things that already exist out there for various reasons. We use our own, mostly because we don't have a single database technology. We have many. So we want to be able to support a single language for database schemas across many different database storage technologies. I mentioned static content. Then you have iOS, so figuring out how to, what is an artifact when you're, well, I think the iOS application is a well understood artifact, but the iOS code or library, software library, is not so much. There are various, people have gone and deconstructed Xcode and Apple's, but we found that that's not 100%. It's like, yeah, it looks exactly like they told me it should look, but it still doesn't. Well, if I tweak this symlink, maybe it'll work. So that's fun. And then I talked about the Hadoop workflows. That's one where it is going to be open sourced as part of the Azkaban open source project. Is a Gradle plugin that will build these Hadoop workflows. I mentioned earlier that we have a richer set. We have a different set of metadata than just IV. We use IV, we don't use Maven, but we could just as easily use POMs. But we need more metadata than what we want or what we can put in IV. XMLs. So we create that and publish that. And that's how we tie into our own deployment tooling. And then I mentioned earlier, elevating the concepts from artifact to product level, grouping things together by Ivy group, Ivy organization. We have some language plugins, Java, Groovy, Scala. We had to add, some of you might have been here last year, and Peter Niederweiser showed an example of how to cross-build Scala. So essentially, it was the first ideas around what is now called variant support. So being able to build Scala code for multiple versions of Scala, incompatible versions of Scala from the same build. So we knew variant support was coming. We were actively involved with Gradleware on variant support, but we couldn't wait. So for Scala's particular, so we added cross-building Scala support. That's something we would have open sourced if it wasn't for variant support, but now with variant supporting Gradle natively, that's a lot better way to do it than these horrible hacks that we had. And then our own version of Spring, unfortunately, which we're rapidly trying to get rid of. Yeah, we have a fork of Spring, very old fork, still on the XML syntax, which is very, very painful. New artifact types, so war, zip, TGC, they're the artifact types that already exist in Gradle, but we have our own customized versions of those. Command line applications are pretty important. Of course, there's the easy command line applications, like an executable jar, I just run it or something. But we have our own command line applications integrated with Spring, with doing very complex things, both in our production environment and in our testing environment. So we needed to have that. That's not something I think is generally useful. It works at LinkedIn. Resources, database schemas I mentioned, Hadoop workflows. We have our own set of, yeah, please.
For the database, with Hadoop, I would imagine you use NoSQL.
Well, so that I mentioned we have many storage technologies, many database technologies.
So that would fall under the same category?
Yeah. So what we want is a common language to talk, or common terminology to talk about all of those different storage technologies. So we want to abstract it. We essentially, whether you are using a key value store or a NoSQL database or just a file system database or a graph database, whatever it is, we have a common language. And it's not like with NoSQL databases, there still is some implicit schema. And so even where we use NoSQL databases, we don't want to think about, they're not totally schemaless. We don't want to, we can't have complete chaos. So you still have to specify a schema or an implicit schema for a NoSQL database. Yeah. Of course, your schema can just be, string or blob, which is working around it, but still, you should think about the structure of your data when you think about NoSQL. Testing is very important. There is no, so when you start talking about software diversity, one of the first things that breaks is testing, because software developers love to bring in new languages and frameworks. They hate having to do any of the tooling or testing for those new languages or frameworks. It's the biggest disconnect. It's like, I can play with this thing. Oh, it's really cool. I can write all this code and ship it. Well, how do you test it? How do you run it? How do you test it? How do you integrate it? Are you getting your alerts, your metrics? That's different. Nah, that's someone will deal with that. So we have a lot of testing methodology built around, again, a heterogeneous world. So you can just test your stuff, even if you're pulling in something new. The, code quality is a big one for us right now. So we have integrated with coverage tools, static analysis tools, style check tools for various different languages. And then we have some frameworks. Avro is very important at LinkedIn. It was funny, I saw the plugin portal talk yesterday, talked about an Avro plugin. So we have an Avro plugin. And iOS and Android, so kind of different, very different ways of looking at different frameworks. So I wanted to dive a little bit deeper into iOS because it's an interesting case study. Not really because it's any different, but it's a good case study of this kind of tier 3 integration where it's hard to figure out, Gradle doesn't understand the code or the structure at all. So at LinkedIn, Gradle provides the glue between CocoaPods, Xcode, and LinkedIn. So what is this LinkedIn? So we have our own way of, and a standard way of declaring dependencies. We have some metadata that says how this code relates to other code. That's important to us because we always want to know how all of our code is related to each other. There are different use cases. For example, the canonical one is a bug fix or a security flaw. If we discover those, we need to know who's using the code that has the bug or the security flaw so that we can push the fix. It's not enough just checking in the fix. You have to actually push that everywhere in order to close the security hole, for example, or fix the bug. So we have our own way of doing that, and then we needed to translate from that to the native way that CocoaPods declares dependencies, the pods or the pod files or the pod specs. So we will take the LinkedIn dependency declaration and a pod template, and we create the pod spec from that using so that CocoaPods can consume it. So that's kind of on the dependency management side. And then on the task management side, we'll have the tasks to manipulate the pod file or the pod specs. Then we'll have the tasks that integrate with CocoaPods and runs various CocoaPods commands. And then we'll have the tasks that uses Xcode. In this case, I made explicit Xcode build because it's run from the command line, not from the actual UI, to execute tasks on the generated Xcode project. So for those of you not familiar, CocoaPods is a way of you declare dependencies. It will download the dependencies from the CocoaPods, put them in a specific structure inside your project, muck around with the Xcode XML project definition so Xcode knows how to pick up those dependencies. So it's essentially, it's a total hack. It's a total glue because dependency management in iOS really doesn't exist. But we didn't want to, at least in the first iteration, we didn't want to hack it up together ourselves since somebody else had already done it. So we'd use CocoaPods for that. I will say, big caveat, we haven't gotten this to work very well yet. It's early days, but it may very well that this just won't work at our scale. It's too brittle. So it may not be something if you were thinking of trying this, this may not be the right approach. We may need to write our own dependency management engine in Gradle in order to do iOS dependencies. But at least for now, we're trying with CocoaPods. So why do that at all? Like, why use Gradle there at the tier 3 at all? It seems, as said, it's a hack. It's not something we normally want to do. We want to allow our developers to hack up stuff and experiment, but we want to kind of be the guardians of good processes. But there's still some benefits here. There's common terminology and process. You can run Gradle build for your iOS project. You know where the artifacts are. You know what the metadata is. You can reason about all of that stuff. Still, I mean, there's a lot of stuff going on under the hood that you can't reason about if you're not, you need to understand it, unfortunately. But it still gives you some of the benefits of a nice, consistent process. You get incremental task execution, although at a macro level. You at least know if no dependency changed, I don't need to do anything with CocoaPods at all, right? That's at least is a powerful concept and something that just comes for free with Gradle. It's not very, it's not micro, it's not at the level where we want it to be, but at least you can tell that. So you have your inputs and outputs and you have some kind of incremental build. And one of the most interesting things is when you do this versus just leaving it off in whatever Bash or Python or you can easily migrate. You can easily start replacing these. So that now if we need to go and implement our own dependency management engine in Gradle, well, we already have the Xcode stuff. So the only thing that needs to change is the implementation behind the dependency management. But the entire interface for developers the build interface stays the same. And that's been incredibly powerful for us. And that's one of the places where we try to pull in Gradle and then replace the underlying implementation to be more and more Gradle aware. And that's what we're planning to do for C++ as well. So we built the initial implementation with Gradle on CMake, creating Ninja, using gperf tools to run stuff, and then as the Gradle native integration matures, we'll keep replacing it. All right, so that's a little bit about what is today. So I wanted to talk about looking forward and how are we going to use some of these Gradle features. Before I do that, I wanted to talk about 3 challenges that LinkedIn has and that I've never been a part of solving before. I have no experience in, so we're trying to figure out how to do it. The first thing that happened was from having development in the San Francisco Bay Area, suddenly we have development across the world happening. People are developing code, they're using our services, our tools everywhere. In India, in New York, in Europe, etc. And that we were totally not prepared for that at all. One of the fun things with hypergrowth is like, we probably should have thought of that. But one very powerful concept that's coming in, one thing we're trying right now, is to provide the locality through tooling. So whether someone is sitting in India or in San Francisco Bay Area, tooling actually makes it look to the infrastructure as if they're sitting in the Bay Area. And it's pretty cool, and it'll allow us to share resources and things like that using tooling. Hopefully that works out. I don't know yet, but maybe next year I can say whether it worked out or not. The other thing is code isolation. So when you start having a lot of these distributed builds, you start sharing more and more infrastructure, you're going to run into the case where people are stomping on each other. A very common example from LinkedIn is somebody wrote some code without realizing it. A side effect is that service now starts spitting out, gigabytes of log files that then gets pushed on the event bus and overwhelms the system and just takes down the system. It happened with relative frequency, and now we're getting, trending towards 0. Another example is where somebody changes some database or some schema and it's backwards incompatible and they don't realize they're working on a shared infrastructure, and suddenly everybody's test break because the schema changed. So there's a little bit of culture change that has to go on there, realizing to people like, you really shouldn't be deleting this. Do you understand the side effects of what you're doing? It's actually the biggest thing. And then there's some tooling we can write, but we also don't want to write we don't want to limit our software developers from doing too many things. So try to work on the culture part. So that comes down to the third challenge, which is just software engineers in general. We are a prickly bunch. Once we've decided that we like something, it is really hard to tear us away from that. Once we've decided we don't like something, it's really hard to get us to like that. I mean, it is just a challenge. If you're trying to disrupt something in this space, right? I mean, it's probably why I totally agree with what was said here yesterday in one of the talks that the IDE wars are over. JetBrains has won. That still means 20 years from now, still going to walk around LinkedIn and somebody's going to be having VI with their own custom macros open, right? Or Emacs with their own. So we move slow. The long tail moves really, really slow. And we just have to contend with that. But that's also, I think, this is part of the fun. But really what it comes down to is there's 3 things to tackle. There's tooling. There's the actual stuff that's running. One thing that is implicit in this conference we don't talk about a lot in very concrete terms is the process. How do you use the tooling? How do you do these things? What are the best practices, etc.? I wish we'd talk more about that. And then the third thing, which is a really hard thing to change, but it happens glacially over time, are the people, right? The software engineers. So we're really trying at LinkedIn to look at all 3 of these and we realize that moving the culture, moving the people is the slowest. Moving tooling is the fastest. We can change stuff, but they all interact. If you change too much, people rebel, or too much too fast, people rebel, right? If you add too much process, people rebel, and tooling is behind. So you have to go in concert. You have to figure out the right pace of change. So what can we do in Gradle to make this a reality, this vision a reality? We need to make it a lot faster. I mean, a lot faster, like constant time fast. A lot of places where currently it's either linear or exponential. So we still, at LinkedIn, because we have these large builds, we cannot use the daemon efficiently. The daemon simply doesn't, it's not stable enough over time. And this is, one of the problems we have is we're still running on Java 6. And the JVM in Java 6 just gets very unhappy when it consumes a lot of memory. Just in general, it gets unhappy. We've seen it in IntelliJ, we've seen it in Gradle, we see it all over the place. So we need to figure that out. We are moving to Java 8 as soon as possible, so that'll be good. A new configuration model is really important, and with that, the constant time configuration, parallel configuration, and then going on to distributed builds. That's really key for us. We've been pushing for that for a while now. Super excited about seeing that later on this year. We keep optimizing both the task graph and the dependency graph. So that's where some of these incremental improvements have come in Gradle from 1.8 to 1.12, is we've been working on features there. And we've been contributing that. And then constant time incremental task execution. Today, Gradle will compute a hash of the inputs to a task and compare it, and the outputs, and compare it to the hash of the last time the task ran and see if they changed. So in order to not do anything, it needs to compute these hashes. It's not constant time. So the more complex your inputs are, the longer it takes to compute those. The longer it takes to compute, the more projects you have, the more memory it consumes, and then you get into GC, and suddenly it takes 10 minutes just to detect that there was nothing to do. So we need to fix that. IDE integration is huge. So it kind of comes with a little bit of phase 2. It doesn't make any sense to integrate something crappy with the IDE. Like that doesn't compute. We need to fix the crappiness first. But once we fix it, once we get more and more, we want to have that available in the IDE so that you can edit your Gradle build scripts. It's DSL aware. It doesn't require any funkiness in the IDE. We have a little bit of work to do to integrate it just with LinkedIn's version of Gradle, or our Gradle wrapper, custom Gradle wrapper. But that is a lot more stuff. Baron over there is going to work relentlessly on that. And then integrating it with Hadoop is something we're doing right now. I'm very, very excited about. It's giving a lot of really nice benefits, so we'll see a lot more around that. Is there, who here has to support or works with Hadoop? Still nothing. Yeah. So I expect over time that would just be, just be as common as developing, say, a war or something like that. You'll have to understand the nature of Hadoop and MapReduce. And then figuring out JavaScript, as I said, JavaScript dependency. Another problem we're having with Gradle today is it's super flexible in some areas and very, very rigid in others. And the rigidity comes when you think about having multiple SCM repos, multiple different types of dependencies. You can't just, it's very hard to change from a binary dependency to a source dependency, for example. It's very hard to change from a local build to a remote build. These things actually don't, the only way to do it would be to have some external scripting engine or some external tool that introspects your Gradle DSL and figures out how to do that. And And it comes back to this inefficiency of software development again. Right? We talk about these large multi-project builds, but no developer ever works on the entire multi-project build. And they actually work on a piece of that multi-project build plus a piece of another one that depends on another one. Right? That's the common thing. And we have no way of modeling that. We have no way of doing that today. So truly dynamic multi-project builds is just going to change the way that we think about these things. We no longer need to worry about, now large repos become a SCM problem, not a tooling problem, not a build problem. That's just, you can have whatever you want in your SCM repo. That's essentially the direction that, Twitter or Facebook are moving in, where they're just push everything into one gigantic repo and then have tooling to let you work on configurable pieces of it. It's essentially the Perforce model, etc. So want to do a lot around that with Gradle. That would be a really game-changing, disrupting feature. And then we also need, Gradle doesn't understand the SAM repos, doesn't understand Git, Subversion, Perforce, Mercurial, whatever you have. So we need some abstraction layers. We need some tooling on top of that. At LinkedIn, we're fine building that, but if there's an open source standard or a open standard that we can follow, we'd love to do that or contribute to. So I mentioned distributed builds is, the next step. All right, once you've parallelized everything, it's time to think about distribution. So I think we've pretty much, there's been a while now since we've gotten to the point where single machines get more powerful. That's one problem. The other thing is it's been a while since we've been wanting to sit at a desk all day. Right? Nobody wants to sit at a desk all day. There's really hilarious, I should have put that up here. It's a hilarious little comic strip. 1980s, you had a really skinny software engineer sitting in front of a really huge computer with a huge monitor. And then 2010, really big software engineer sitting in front of the little tiny, laptop, right? So that's the way. Let's hope we can. The other thing we'll deal with, but this machines getting smaller and smaller and smaller is something we want. We want people to be able to sit at the airport, sit in their couch, sit in a beanbag, walk around and develop software. We don't want to be tethered to these large machines at our desks. So we want to distribute it on a cluster. We want to have the concept of a build as a service, a build cloud, a build farm, whatever you want to call it. We want to be able to throw hardware at it and make it go really fast. Automate the provisioning. So Gradle, just like Gradle today, will take up more machine resources as it runs. If it needs it, it should be able to take up more machines if it needs it. Here's what I have available, here's what I need to do. I'll take the optimal set and I'll run on that. And then I think a nice side effect of this, or really it will come before this, is we'll finally have a way to do artifact sharing at scale. Talking about inefficiencies in the system, you're typically sitting around a team, and a team can be anywhere from 3 people to 50 people. And you're doing the same tasks on the same code all day and the next day, right? There's very little that changes between one developer and another developer. So if we could find a way to seamlessly share intermediate artifacts, intermediate work among people that are doing development, really doing that seamlessly and well. There are protocols out there that will help us do that, BitTorrent, etc., distributed cache technologies. We can really change the way, really now it's all an underlying abstraction layer. It just runs and you have everything available for you on your development machine. So very, very excited about the distributed build automation. So what's the vision? At LinkedIn, this is where we want to get. This is what we want to do in anywhere from 2 to 3 years from now. The Gradle daemon in watcher mode is running whatever development environment you're on. And that takes care of actually 80% of all the development use cases. Right? You're changing some code, it runs some incremental tasks, everything is good. You've got total instantaneous feedback whenever you're changing something, whether you ask it or not, how you configured it, it all just runs. And then you have distributed builds and the LinkedIn deployment tooling. So talking about some of these abstraction layers, one thing we're doing is in a service-oriented architecture, you can deploy your service under test, the service you're changing. You're running it against a fabric or a shared stack that's running all the other services. So you only need to deploy what you're actually changing. So I know Google has a similar model. So the distributed builds and the deployment tooling they kick in when you hit a certain threshold, right? If Gradle or whatever it is, LinkedIn tooling detects that you've not made enough changes or you're asking for a complex enough task to where I should start using the build as a service, start using the cloud, I'm going to go off and I'm going to start doing that, right? One of the saving graces for us is we're a web company, right? In the end, what ends up happening is people will open a browser and they'll hit the service. They'll hit some URL. You can do that. It doesn't matter to people whether that service is running locally, whether that request routes a bunch of other requests to other services. The interface for testing and for development is very easy. So we think we can do a lot of these things just completely untethered. So that really is the vision, is that a LinkedIn developer anywhere in the world, on their tablet, on their laptop, on their desktop, they can just go off, they have the same power available to them everywhere. And the tooling intelligently under the hood takes care of build automation, deployment automation, testing, verification, all of these things in a totally dynamic way across repos, across projects. And that really it removes the friction in the development system. It enables these very, very expensive developers to be productive. And it really just changes the way that people think about cost in software development. Because now releasing, deploying, all of these things are cheap concepts. So when something is ready to go, when you want to make a little tweak, you make it, it's easily available, there's no cost, there's no friction in the system. So that's how we get there. All right, that's what I had. Any questions? Yeah?
Can you elaborate a little bit on the reasons why you're not using the native code feature in Gradle?
Our work predates Gradle really having a native feature. At this point, there are few sticking points, small ones. I asked actually Daz about that during the talk yesterday, was the Ninja integration. So that's, C++ developers are very latency sensitive. They, like spawning a JVM is just, that's too much for them. 1-2 second latency is too much for them. But that's part of we're not trying to change too much too fast for them. So we added the Gradle integration on top of CMake and Ninja for now. And then slowly over time, we're going to add more and more goodness. And as the Gradle native integration gets better and more full-featured, we'll be using all that stuff. At the same time, we think that the Gradle native integration has some things that are uniquely valuable, like the variant support, architecture support, etc. So we think we can convince people that this is the right way to go. We will use it. I mean, there's no, if the roadmap doesn't fit, then we'll try to influence the roadmap so that it fits, because it's super cool. And C++ is, or I guess native code is really important in there. Like once we have every single request coming into any of our products go through multiple C++ layers. First of all, it hits C++ on to detect things like denial of service, kind of the first thing that a request hit. And then there are certain, through JNI, pieces of C++ that sit and do very latency sensitive, things that happen very frequently at the bottom of our stack. So really important stuff. Yeah. Any other questions? All right, thanks everyone.